Last presentation of the day, so sorry for taking your lunch a bit. But it's actually good to be in the end of the conference because we are talking about ejection of planets and making free-floating planets and then talking about how they live out there. But if you think about it, rogue planets are pretty lonely, right? They just leave their family, go away. And what I'm going to tell you about is that they actually have a new hope. They can actually come back. They can be recaptured. So let me tell you about how free-floating planets, or general rogue worlds, small planetesimals mostly, can be recaptured into stellar systems and become planets or planetesimals in these systems. And even more importantly, how rogue worlds might be actually much more important than you think and might be the driver of planet formation to begin with. So let me see how it goes. So catch me if you can. I'll also tell you about how all that related to pandemics. Surprisingly. Okay. So what happened here? I don't know. Okay. But so in principle, we have several ways of getting planetesimals and planets being captured. And I'll tell you about one of them. And if I have time, probably I won't, I'll just mention the other ones. So you all know about planet formation. We have problems with planet formations and, of course, suggested solutions. One of the main problems is the meter-sized barrier. So small planetesimals, when they collide, if they're big enough, they start to destroying each other. So it's actually very difficult to make them grow beyond kind of tens of centimeters. So that's one part of the meter-sized barrier. The other problem is the gas drift. So kind of small planetesimals see the gas drag and then the in-spiral in very fast, and they actually end their life in the star instead of actually building up planets as we want them to do. So these are two parts of the very well-known album. And of course, when you have gas drag, which I'll discuss more a bit later, this is how the drag force works. So you can see how it's related, of course, to the size, of course, of the planetesimal, the A. And the bigger you are, of course, the size ratio to your mass ratio become smaller and smaller. So it's more difficult. You actually have a less effect on the bigger planetesimals. The small planetesimals are strongly affected. Last problem with meter-sized barrier is that actually small planetesimals are also eroded. As they see the headwind, it takes part of their material and they actually become smaller and smaller. So again, it's very difficult to grow them. Okay, so we have many problems with growing planets at the early stage. And of course, we have very suggested solutions like streaming instability and dust and migration traps. So, and these might work, but they might actually require very highly or fine-tuned conditions. So it might be actually very rare, only very metal-rich systems or things like that. So it might work, but it might actually be very challenging and only works at very fine-tuned conditions. So why am I talking about all of these issues? Because a few years back, when I was a postdoc in the CFA, I was thinking of how we can actually use these problems and make them actually solutions. For example, how gas drag can actually help us instead of making a problem. And I was talking with Ruth and other people in the CFA, and started to look about how you can actually help capture planetesimals through gas drag. For example, you have a planet and you have a small planetesimals. They go close to each other because they have differential gas drag between the big object and the small object. One of them, the relative velocity can be dissipated and it can become bound, and it can actually then accrete and grow. So we actually started working on that, and we put some stuff. We were a bit slow on some aspect, but you probably already know that. This is now today called pebble accretion. But then I was thinking, okay, can we actually use it in larger scale? Can gas drag help us capture things not into planets or protoplanets, but into stellar systems? So we were already told by Amaya that planetesimals are scattered all over the place. We have tons of planetesimals. We even see interstellar planetesimals, comets coming into the solar system. So we know they are out there. We even know that they're actually going through the solar system today. But if you think about it, in the early solar system, we had a protoplanetary disk, a gaseous disk. And we just told you that gas drag is actually effective, even too effective, the meter-sized barrier problem. But if it's too effective, maybe it can help. If you have a planetesimal going through a disk, it actually get dissipated, its velocity. So it might actually become bound and become part of the disk. So it's kind of a butterfly network. You can go away and it kind of captures planetesimals on the way. So we actually tested this and tried to look on the calculation. So as it turns out, Okay. So as it turned out, we actually can look at the same kind of ideas, right, of gas drag as the same kind of equations, and you try to see if a planetesimals comes in a solar system and goes out. But if you have a disk, you have a dissipation, so you can actually calculate it. First of all, you can estimate it analytically, and it depends. You remember that the disk have higher density closer in and less dense out in the outer parts. So it's easier to capture in principle closer in. Also, the velocities are higher, but you have higher densities, so a better chance of capturing it. So in order to capture at some separation, it really depends on also the density distribution of the disk, the incoming velocities, and some kind of parameters that need to calculate. So if you think about the gravitational focusing, in order to capture close in, gravitational focusing is more important than going through the outer part. So if you actually need to come very close in, for example, if you are bigger planetesimals, in order to get enough gas drag to be dissipated, you need to actually go closer in the denser region of the disk. So you need kind of, in this region, gravitational focusing is more important in terms of the probability of getting this than a geometric one. Anyway, we can actually do this calculation, both analytically and in simulation. We can actually do an simulation, add gas drag effectively on planetesimals as they go with the disk, look on planetesimals coming from all directions, different cross-section, in some kind of relatively isotropic distribution. And what we see is the following. So this is the size of planetesimals. Here it's in meters, okay? And this is a fraction of them that are getting captured. So what you can see that small planetesimals are easily captured, right? A huge fraction of them, which is not surprising. Just think about centimeter or millimeter size in the disk. They're completely embedded in the gas. Just follow it. So if they go through, they just captured. Bigger one, it's more difficult. It also depends on the regime, whether gravitationally focused or not. But it turns out you can actually get non-negligible fraction, especially if you remember that there are tons of those free-floating planetesimals out there. And if you actually want to capture like kilometer-sized things that are beyond the meter-sized barrier problem, if you capture big things, they might actually help you in seeding the disk with basically the seeds of planets. Because if you have a kilometer-sized planetesimal, it can help you grow to larger sizes. Okay? We can even estimate it, even some dependence on the distribution of the size function or mass function of planetesimal. Amaya was talking a bit about that. We have some kind of lower estimates, but if you actually account for the observation of interstellar comets, which have higher rates than what people expected before that, this actually even go to these larger numbers. So we have pretty large number, potentially tens or even thousands or tens of thousands, like kilometer-sized things that can be captured in the early days of a protoplanetary, when protoplanetary disks still exist. Great. So in principle, once we put a small number of kilometer-sized planetesimal in a protoplanetary disk, they start growing easily. They don't actually go into the star. They actually serve as the seeds of planet formation, and they form a whole planetary system. So in a sense, we actually seeded the system, and we solved the meter-sized problem, right? We just get the planets from seeding it from the outside. So this is really literally out-of-the-box thinking, right? We bring it from the outside, and that's great. So cool. So captured planetesimals serve as seeds for planet formation. So is there any problem with that? So there's an obvious problem. No one? Nothing?
Why is that all the time? Never start.
That's one problem. The other? Oh, the chicken and egg problem. Thank you. Okay. So yeah, it's Feynman joke about the turtles going all the way to. So okay, but I need the first ones to actually have them. You need these planetesimals to be there in order to capture them. So I didn't solve everything. I just kind of moved the problem elsewhere, which relates, of course, to Bruce's second question. Okay. So this potentially doesn't solve anything. We still need it. And right, how do you actually get this kilometers of planetesimal? We said we need potentially just fine-tuned conditions to begin with all of this process. However, now we go to the pandemic aspect. Okay, so we can actually make this chicken egg problem not a problem, but making it exponentially small in a sense, or easy to solve. You can actually make fine-tuned conditions to be good enough. How do we do that? Think about the pandemic. I don't know if anyone has thought about that in the last few years, I don't know. But in principle, right, all we need is patient zero somewhere over there to actually have the whole world having having the disease, right? So think about the same thing in relation to these planetesimals, right? Each planet-forming system, right, it ejects many planetesimals, right? About Earth's mass of planetesimals. So if even more than one of those being captured by another planetary system, it also forms planets and starts ejecting its own planetesimals, and so on. So basically, it's like a pandemic, if you can think about it, right? We start with ejection of some planetesimal, and then we have these kind of susceptible systems where we actually have a disk. We have stars which don't have disk because most of them are not in the young age that they still have a disk. But those that they have a chance of actually being captured, actually pretty good chance if it actually goes through. And if they do, each one of them doing that, and that each one of them that. So we actually get an exponential growth of all of these things. So in a sense, we need only a small fraction of systems to actually start their planet formation by themselves. And from there on, if you can actually get this R larger than 1, the kind of how many they actually can give them planetesimals, we can go all of these things. By the way, there were suggestions about how you can even help, because maybe even molecular clouds might even capture even more planetesimal, not just a planetesimal disk. Not going to that, it actually doesn't work that well. But even just with the disk himself, you can think about that, and you can still continue to think about this, in a sense, pandemic model, and think about clusters. This is actually global cluster. We should actually talk about young, kind of smaller clusters. But in principle, if you don't need really getting all of the stars to get planetesimals. If you talk about clusters, and most stars actually form in some kind of clusters, it's enough to effectively have one of them being captured and start planet formation and eject itself. Because of this very close, dense environment, they will start infecting all the other ones. So all you need is actually having a few in a cluster to start in that. And of course, then all the cluster stars are infected, send their planetesimals, and can actually go through other clusters. So it's really like a pandemic. If you think about like a dense city versus kind of a rural area that people don't actually interact, all we really need in order to actually get really pandemic, thank you, is getting this even to the bigger ones. And since all stars actually do form in these kind of dense areas, less or more, you can actually get it. So now actually what I'm working on this follow-up paper is actually do the exact calculation in the galaxy, including star formation history, but it actually seems to work. By the way, today, irrespective of that actually started all of planet formation, today, given the number of interstellar planetesimals that we see, every single star should have actually interstellar comets coming in and being captured. You can see it, right? We already have a few years, already a few of them going in. If they actually have protoplanetary disk, some of them would have been captured. So today, they're certainly going like this all the time, everywhere. It's only the question whether early on it actually even started this whole formation, or is it only now that it actually happens? So with that, I basically start finish and say, okay, so actually fine-tuned condition can be very robust. We have fine-tuned conditions are actually fine, okay? So effectively, by the way, there's other issues with that. How do you actually form all the many asteroids that we see if you only capture a few of them? That's not a big problem because once you start planet formation, you have collisions, you have disruption, you actually form smaller things from even bigger things in some sense. I won't go into that because I'm out of time. I just mentioned this, of course, also true for panspermia. If you have living thing, you can also have the same thing. So it's actually a very efficient mechanism for panspermia. So if we do have living thing out there, it could actually infect other places. So I'll finish with that. There are other capture mechanisms which are really interesting, but I don't have time. You can ask me about them if you want, and I'll just finish with those conclusions. Thank you very much.
Really fun talk. Question for you: what is the time scale for sort of the exponential turn on in your exponential model? When do you have to start with the first seed to make sure that we actually get all the exoplanets we see in the galaxy?
Okay, so this is actually the kind of the calculation I'm starting doing exactly with star formation history for the whole galaxy, but it seems you can actually do it relatively early on, at the scale of, I don't know, 100 mega years or so, the early galaxy evolution. You don't need kind of giga years. Otherwise, you would see exactly right that old systems don't have planets and young systems do. But if it's young, if it starts actually early enough, which it does, then it should work. Remember that in clusters, it's enough that one in a cluster of 1,000 is enough to actually fill in the cluster, and then all the clusters and things, except all the exponential stuff. So you do, of course, need some of them to be rarely formed by themselves, okay? But very small fraction of them, and that's enough.
So do you, are you claiming that you need to have like one of these happen in each cluster, or it just needs to happen in a cluster once, and then that can trigger other regions?
Yeah. So we have the capture like in cluster, which is very efficient, and then we have the capture through kind of those that actually go in the field, and then they have a small, relatively much more chance of actually getting other stars. However, these other stars are usually also starting clusters. So yes for both. In the cluster, it actually works easily. Between those in the field, it's enough that you actually do it into another cluster. So you don't necessarily have it in the other cluster. So you do need it in the first cluster. Later on, the exact numbers, this is what I calculate with star formation history and the spatial evolution for the galaxy, whatever. Now we go into the details. To the order of magnitude, it can work. You don't need in every single cluster. You need only the early ones. But yeah, there's caveats. I need to do the exact final calculation. I'm almost there.
Okay, so like you could seed it in Taurus, for example, which has very low density and not a lot of stars to.
Yeah, because also remember that they are very low velocity, so it's much easier to capture them. So yes, much smaller number of stars, but the velocities are low. And actually, I got some help from the previous talk. Most of the objects which are free floating actually are staying in the cluster and even the central part, which are even denser. So that even helps more.
I think we need to close out. So we'll thank our last speaker and all of the speakers of this session.